Hello and welcome to this video on calculating parallel impedances using complex numbers. So hopefully you're familiar with the idea of calculating resistors in parallel, and we're going to be using similar methods in this video, but we're going to be looking at examples where we don't just have resistors in parallel, but we might have some complex circuit elements, some reactive components such as inductors and capacitors, and how that changes our approach. So to begin with, let's just review very quickly how we do calculate resistors, ordinary resistors, in parallel. If you're not sure, we have a previous video where we cover the basics of this, but if we have an arrangement such as this, where we've got two resistors in parallel like these, then we know that we can say 1 over what I'll call the total resistance RT, 1 over RT, is equal to 1 over R1 plus 1 over R2. And providing that there's only two resistors in parallel, we can cheat a little bit. There's another formula we can use, which is a bit more convenient. It's this one here. RT, the total resistance, is equal to R1 times R2 over R1 plus R2. Just remember, you can only do that with two resistors in parallel. If you have 3 or 4 or more parallel circuit elements, you can't extend this formula, but you can extend this formula. We can say 1 over R1 plus 1 over R2 plus 1 over R3 plus so on and so forth. But anyway, our formula above are only dealing with resistances at the minute, because we're talking about these R components. And this is quite useful, we can adapt these formulae to be in terms of impedances also. So I could write 1 over ZT is equal to 1 over Z1 plus 1 over Z2 and so on. Or again, if there's only two impedances, we can say ZT is equal to Z1 times Z2 over Z1 plus Z2. So we're not really introducing any new formulae here. We are just using the same formulae as we've seen for parallel resistors, but we're going to see how the method changes a little bit when we involve complex numbers. So let's have a look at an example here, and let's say that we have these two components. We have a resistor of 40 ohms and an inductor whose reactance XL is 60 ohms. It's an imaginary term, reactance, so it's given a J as our imaginary unit here. J 60 ohms is our reactance here. So at the beginning, we gave sort of two alternative formulae that we can use. In fact, in this video, let's use both. We'll do the same example twice, but we'll hopefully show that the two formulae give equivalent results, and then you can sort of decide which one you prefer. Let's start with this one here. 1 over ZT equals 1 over Z1 plus 1 over Z2. And what we can do is then substitute in our values here, because we know that Z1, we're calling this 40 ohms. Z2 is our reactance, J 60 ohms. And so we have 1 over ZT is now 1 over 40 plus 1 over J 60. So at this point, I want to remind you of a very useful identity, which is going to come up a lot in this video, which is to say this: it's 1 over J is equal to minus J. 1 over J is equal to minus J. So in our example here, let's just pick on this 1 over J 60 term for a second. Just over at the side here, let's say that 1 over J 60, we could say that that's the same as 1 over J times 1 over 60. And we've just said that 1 over J is the same as minus J. And so that could be expressed as minus J times 1 over 60. Or we could say that that's minus J over 60. These all mean the same thing. And so again, we'll return to our equation. We'll take that into account. We'll say that 1 over ZT is equal to 1 over 40 plus minus J 1 over 60, or we could simplify that a little bit. We could say 1 over 40 minus J 1 over 60. These are equivalent. So at this stage, we can see that we've calculated the inverse of ZT, or we've set up an equation for the inverse of ZT, 1 over ZT here. otherwise known as the admittance of the circuit. But we need to take the reciprocal of both sides in order that our equation is in the form of zt. We're not too bothered about finding out what 1 over zt is. The objective is to find zt. And so if we take reciprocal of both sides, 1 over both sides, 1 over zt is just zt. And 1 over the other side, we end up with 1 over 40 minus j 1 over 60. Now here we're dividing by a complex number. And we have two options. We can either convert to polar form to do this division, but this generally introduces rounding errors, which we don't want. So the other alternative is to keep this in Cartesian form using real and imaginary numbers with our j notation here. But we're going to use something called the complex conjugate to help us find a result. What do we mean by the complex conjugate? Well, the complex conjugate is to take a complex number, like we have on the bottom of our fraction here. We have a real number and an imaginary number. Together they make our complex number. And the complex conjugate is simply that complex number with the sign of our imaginary number changed. And so here, our imaginary number j 1 over 60 is negative. It has a negative sign. We're going to change that to a positive, and that's the complex conjugate. If it was positive to begin with, we'd make it a negative and so on. We're going to multiply by a fraction that has the conjugate on the top and the bottom, and so we have something that looks like this. We have that denominator with the sign change. It's now a plus on the top and the bottom here. And what we can do is we can multiply these numerators on the top and denominators on the bottom. And so if we set that up, we have something that looks like this. The top, these numerators are easy enough because we're multiplying by 1. And so we have that conjugate on the top still, 1 times this numerator here. On the bottom, we have what I've set up for now is these double brackets here. We've set up the original denominator multiplied by its own conjugate. Now, one of the useful things, if you've not seen our previous videos on multiplying out complex numbers like this, is that when you multiply a complex number by its own conjugate, the result is always a real number. You shouldn't have an imaginary number in the result. And we'll hopefully see that in just a second. So multiplying out the bottom of this fraction here, I tend to use the acronym FOIL, which stands for first, outside, inside, and last. If we multiply out the first terms, what I mean is the first terms in each of the brackets. So the first here will be 1 over 40. The first term in the second bracket would be 1 over 40. We have 1 over 1,600. The outside two terms, or the outermost terms, are the 1 over 40 multiplied by j 1 over 60. And here we get j 1 over 2,400. Inside, or the innermost terms, we have minus j 1 over 60 times 1 over 40. And so we get minus j 1 over 2,400. And then the last two terms, the last in each bracket, would be the minus j 1 over 60 times plus j 1 over 60. And that gives us minus j squared times 1 over 3,600. Okay, two things at this point. First of all, you'll notice that these j terms will hopefully cancel each other out because we have plus j 1 over 2,400 minus j 1 over 2,400. They're going to disappear. Second thing is recall the definition of j. J is equal to the square root of minus 1. We've not really gone into that much in this video because we talk about it a lot in other videos, but j is defined as the square root of minus 1. And so j squared must be minus 1. So what we have here, looking at our equation here, is minus 1. In other words, plus 1. And if we multiply something by plus 1, it doesn't change. So really what we can do is we can say that this whole term here, minus j squared 1 over 3,600, is just plus 1 over 3,600. That j squared term becomes a minus 1, and minus 1 is just a plus. So we have plus 1 over 3,600. And so let's simplify all of that, take into account these two terms have gone. The j squared term has become positive. We end up with something like this. We have just 1 over 1,600 plus 1 over 3,600 on the bottom here. And if we add those two together, they're both just real numbers. We get 13 over 14,400 as the denominator of the fraction there. And you'll see that's just a real number. There's no j terms anymore, and that's because we've multiplied by the complex conjugate. Let's just tidy this up a little bit, because what we have here is what's called a complex fraction. It's nothing to do with complex numbers. It just means to say that we've got a fraction inside a fraction, which is not very tidy. We have this fraction as the denominator. So what we can do is, rather than say we've divided this complex number 1 over 40 plus j 1 over 60, rather than say we divided that by 13 over 14,400, we're instead going to multiply it by its reciprocal. So that's to say that we're going to see something like this. We're going to multiply by 14,400 divided by 13. We've flipped that fraction upside down, and we're multiplying rather than dividing. And if we multiply out all those terms, multiplying 1 over 40 by this fraction and 1 over 60 by this fraction, we can multiply out that bracket. We can say that we have 360 over 13 as our real component, plus j 240 over 13 as our imaginary component. And that's as rational numbers there in fractional form. We could round that to decimals. We end up with something like this, 27.6923 plus j 18.4615 ohms as a decimal. So unfortunately, you can see hopefully that combining complex numbers in parallel can be a lot more complicated, unfortunately, than combining just simple resistors in parallel. We mentioned at the start there was two methods. We've used one of them there. Let's have a look at the other one as well. And it was this one here, ZT equals Z1 times Z2 over Z1 plus Z2. Let's use the same values, hopefully get the same results. So putting these straight in, we have 40 times J60 over 40 plus J60. You'll recall our original values. We had a 40 ohm resistor and a J60 ohm inductor. And so we've put those same values in there. 40 times J60 on the top, we get J2400. And 40 plus J60 on the bottom, we can't really do anything with that. It's a complex number in Cartesian form. What we can do is use the same trick as we used last time to get a real number on the denominator of our fraction here. We multiply by the complex conjugate. And so what we can do is take this denominator, this complex number 40 plus J60. Its complex conjugate is going to be 40 minus J60. Remember, all we do is change the sign. And we multiply by that conjugate top and bottom. So we have something that looks like this. And when we multiply these out, let's write this in sort of bracket form. We have J2400 multiplied by 40 minus J60 on the top. We have 40 plus J60 multiplied by 40 minus J60 on the bottom. The top, or the numerator in this case, we're going to multiply these two terms, 40 and minus J60. We're going to multiply those by J2400. Well, J2400 times 40 is going to give us J96,000. And J2400 times minus J60 is going to give us minus J squared 144,000. Now remember what we mentioned about J squared before. J squared is minus 1, and so minus 1 is plus 1, and plus 1, we don't even need to write it. When we multiply something by plus 1, it doesn't change, so we just have a real number of 144,000. And so we could write that as 144,000 plus J 96,000 was our other term there. On the bottom, we have, using again that FOIL acronym, the first term, 40 times 40 gives us 1,600. The outside or outermost terms, 40 times minus J60 is going to give us minus J 2,400. The inside or the innermost terms, plus J 2,400. And the last terms, J60 times minus J60 is going to give us minus J squared 3,600. Remember what we said, these 2,400 terms are going to disappear, minus 2,400 plus 2,400, those J terms are going to go. J squared is minus 1, so minus 1 is plus 1, so just plus 3,600. And we have 1,600 plus 3,600, which gives us 5,200. So we could simplify this whole thing like this. We have what we had on the top, 144,000 plus J 96,000 on the top, divided by 5,200 on the bottom. And in lowest terms, we could say that that's 360 plus J 240 over 13. Or we could break those into separate terms, 360 over 13 plus J 240 over 13. Or we could round to decimals and we could say 27.6923 plus J 18.4615. And that's an impedance in ohms. Again, hopefully you'll notice that our result here matches the result that we used in the previous method. So we see here that both methods, we've used two methods here, they both typically involve use of the complex conjugate. There are exceptions where no resistors are involved. We'll see another example in just a second. But we also see that both give the same answer. So whichever method you use is typically a matter of preference. Let's have a look at another example, and this is an example where both of our parallel components are reactive. We've got a reactive component, an inductor here at the top, J50 ohms, and we have a capacitor which is also a reactive component here, which is minus J30 ohms. And we've got this sort of series parallel arrangement because we also have a resistor which is connected in series to these two components in parallel. So let's just look at these two parallel components to begin with, and we'll combine these two reactances into one impedance, and we'll call this ZLC, Z for the inductor and the capacitor, ZLC. Now what we can do to calculate ZLC, if both of our components are reactive, as they are in this case, in this parallel arrangement, then we can kind of cheat a little bit. We can ignore the J terms, the imaginary terms in each of these, and we could work these out as though they were two resistors. So to illustrate what I mean, let's use this formula here, Z1 times Z2 over Z1 plus Z2. And let's just substitute these values in without the J terms, and we see something like this. And the result that we get is minus 75 ohms. And all we do is we remove these J terms at the beginning. We'll just substitute these back in place again. And so now we have minus J 75 ohms. Now, that's kind of a cheating method, which is fine. Let's prove that by working it out as though we were working it out properly with the J term, and we'll see that we actually do get the same answer. And we saw above that we can use either formula, but we'll just use the one for this example. Let's use this one here. 1 over ZT, or 1 over ZLC in this case, is going to be 1 over ZL, the impedance of our inductor, plus 1 over ZC, the impedance of our capacitor. And putting some values in, we have 1 over J50 plus 1 over minus J30. So remember the little identity that we saw before, 1 over J is equal to minus J. And conversely, 1 over minus j is equal to plus j. And so what we can write is something that looks like this. We can say that this is the same as minus j 1 over 50 plus j 1 over 30. So that 1 over j is the same as minus j, and that 1 over minus j is the same as plus j. And what we can do is we can draw out j as a common factor here. We can pull that outside of our fraction, so we can say that this is the same as j minus 1 over 50 plus 1 over 30, and minus 1 over 50 plus 1 over 30 is 1 over 75. So at this point we've worked out 1 over ZLC, and we've said that 1 over ZLC is j 1 over 75. We have to find the reciprocal of both sides. So 1 over ZLC will just give us ZLC. 1 over j 1 over 75, well, 1 over j is minus j. 1 over 75 is going to be 75. And so our final result for ZLC is minus j 75. So hopefully you'll see here that what we've got is something that matches what we found at the very beginning when we work this out by ignoring the j term altogether and then just adding the j term in at the end. We got a result of minus j 75 ohms. Here we've sort of derived that fully using complex numbers. We see that we do actually get the same answer. So if you have a situation like this where you have two impedances in parallel, it isn't necessary to do what we've done here. We can just use that sort of cheating method that we saw at the very beginning. Finally, though, going back to our previous diagram here, the example that we started with, it's not just these two parallel components. We have this 47 ohm resistor added on the end. Well, that's nice and easy for us. When we add things in series, we do that. We just add them. And so we have here now our ZT, our total resistance for the whole arrangement here, is going to be our resistance plus this impedance ZLC for these two parallel components. And just adding those together, we have 47 minus j 75 ohms. Remember, ZLC was a negative number, so even though we're adding, we have a minus here. And that gives us the total impedance for this whole circuit arrangement. So I hope you found this video useful, just taking the basic concepts of resistors in parallel, but applying them to some examples of reactive components as well.